example, which is the special linear group over the rational numbers. So let me start with some generalities. We have a connected semi-simple algebraic group defined over the rational numbers of positive rank, and G denotes the group of real points of this algebraic group. So it's a real Lie group. We choose a maximal compact subgroup and consider the corresponding symmetric space. This is contractible, and its dimension is the dimension of G as a Lie group minus the dimension of the maximal compact subgroup. And we take an arithmetic torsion-free subgroup of G. We can view it as a discrete subgroup of the real Lie group G. And the group gamma acts properly and freely on X. So we get, by taking the quotient, the smooth manifold of dimension equal to dg. This manifold is non-compact, but it has finite volume. Due to the non-compactness, we choose specific compactification, which is very well suited to looking at the cohomology of these spaces, namely it's the Borel-Serre compactification. First, Borel-Serre enlarged the space X to the space X bar, on which the group gamma acts again. And then they compactified this or enlarged it. And after taking the action on this X bar, they get a compact manifold with corners. And the inclusion of X mod gamma into this compact manifold with corners is a homotopy equivalence. Consequently, the homology or cohomology groups of these two spaces are isomorphic. This is the reason why this Serre compactification is well suited. And the boundary consists of a finite union of faces following the notation used by Borel-Serre. I call them E prime Q, where Q runs over a set of representatives for the finitely many gamma conjugacy classes of proper parabolic Q subgroups of G. Passing now to the cohomology, I take a coefficient system which comes or originates from a finite dimensional, irreducible algebraic representation of G. E is a complex vector space. And I can look at the group cohomology of gamma with values in the coefficient system given by, or with values in the gamma module given by E. But I prefer to look at it as a form of de Rham cohomology. So this is coming from the complex of E-valued gamma invariant differential forms on X. And following Borel-Serre, we know that the cohomology groups vanish above the degree given by dg, which minus the rank of the algebraic group P, which is also the cohomological dimension of the arithmetic group gamma, which is a notion or concept coming from geometric group theory. If we take the example, the example of the special linear group over Q, and we take an arithmetic subgroup, like a principal congruence subgroup, for example, the cohomological dimension is n times n minus 1 over 2. And in the last 2 or 3 decades, or even 4 decades, I would say, one had the tendency, or the idea, to interpret these groups in terms of the automorphic spectrum of gamma in the algebraic group G. And following the work of Franke and others, one has a decomposition of these cohomology groups into the Cuspidal cohomology. These are cohomology classes which are represented by Cuspidal automorphic forms for gamma in G for G with respect to gamma. And the second summand is built up by cohomology classes which can be represented by forms arising from Eisenstein series for G with respect to gamma. I will go into more details with regard to the second summand in a moment. Namely, this second summand can be further decomposed according to the associate classes of proper parabolic Q subgroups of G. A given class, represented by a proper parabolic Q subgroup, falls into finitely many GQ conjugacy classes. So we have here the further decomposition, where each of these summands indexed by the associate class is built up by Eisenstein series. This means appropriate derivatives of these or residues of such at the suitable multi-valued complex parameters. And these Eisenstein series are attached to Cuspidal automorphic forms on the Levy components of elements in the associate class of P. And the general question one can ask, do we have any vanishing or non-vanishing results for each of these summands? If you have some, in particular, if you know that something is non-vanishing, can you describe in more detail the internal structure of these summands? And if you lean to the computational side, you can even ask, what is the size of the summands? And I will focus in this talk as an exemplary case on the special linear group, and in particular, the degree given by the cohomological dimension of gamma. This is the top degree in which the cohomology does not probably vanish. Of course, you may ask, why is Schwermer looking at this specific degree? In recent years, some topologists looked exactly at this degree of arithmetic groups, and they used the relation of the cohomology group of gamma in this top degree to the Steinberg module of the algebraic group G. So to have the relation with regard to gamma, you have to take the Steinberg module of the algebraic group G over Q is given by the reduced homology in degree rank of G minus 1 of the Tits building with integral coefficients. And on this, you have an action of the algebraic group G over Q, and therefore also an action of gamma. And you have to take the co-invariance. And then you get an isomorphism between the top degree cohomology of gamma and this other group. The first person or people who used this identification were Ronnie Lee and Chaba in the mid-70s. Afterwards, Avner Esch and also others. So it was picked up again by topologists, and they tried to say something about this co-invariance in the Steinberg module. But they did this for the full group, SLN over the ring of integers, for example, or GLN over the ring of integers. Or they did this for the congruence subgroup, because you can, of course, you have an action on the Tits building, and you can take the quotient modulo the action of a gamma congruence subgroup. And then they showed that this projection from the Tits building to the quotient is surjective. So the size of this quotient gives you a lower bound for the size of the cohomology group in the top degree. And when I saw these results, I thought, okay, what can be said from the side of Eisenstein series and cohomology of arithmetic groups in terms of automorphic forms on these results? In particular, in one of their papers, they remarked that in the case SL3, the results which were obtained by Ronnie Lee and myself in the mid-70s were already better in size than their bound. So I thought, okay, a good chance to see if this result can be enlarged or extended to the general case. So let me give you an illustrative example. We take n larger or equal than 3. We take a principal congruent subgroup of a prime power. And then, with the help of the construction of Eisenstein series, you can show that the dimension of the top degree cohomology of gamma q is larger than the sum of this expression here. I will explain later on where it comes from. This expression here. And this here is the genus of the compact Riemann surface, which is attached to the congruence subgroup of level Q in SL2 over the integers. And then you have a term which also depends on the level Q and which originates from whatever we know about the Cuspidal cohomology of congruent subgroups in SL3. And later on, I will explain to you that this is not much, but at least we know a little bit. So I'll explain this here. So let me go now into more details. So in general, you have a projection of a given parabolic to the quotient modulo the unipotent radical. And this induces the vibration of the phase E prime P, which is essentially given by the real points of the parabolic modulo the split component, divided by the maximal compact subgroup K intersected with P, modulo the intersection of gamma with P. And then you go to the base, which is a locally symmetric space attached essentially to the Levy component M of P, modulo the action of the intersection of gamma with M. You have to be a little bit careful if you are working with a quotient or if you lift this M into the group P. Yeah, this is a slightly subtle point you have to look at. And the fibers are compact. They're coming from the unipotent radical modulo the intersection with the arithmetic group. The spectral sequence in cohomology degenerates at A2. So the cohomology of the phase is given by the cohomology of the base with values. Now you might be surprised if you hear this for the first time that you don't have the cohomology of n modulo gamma n. But in the case of unipotent groups, if you pass to cohomology, the arithmetic group doesn't play any role anymore. So this cohomology of this space here is isomorphic to the cohomology of the Lie algebra of the real points of the unipotent radical. And you can even have this isomorphism over the rational numbers. So this, if you have here some rational representation, then this, of course, is also a rational representation, if you like. So I said before, Eisenstein cohomology classes, and if you're familiar with this whole business of Eisenstein cohomology classes, you know this very well, are constructed with the help of Cuspidal automorphic forms on the locally symmetric space, which is the base of the phase E prime P. From the representation theoretical point of view, these Cuspidal cohomology groups decompose in terms of relative Lie algebra cohomology as a direct sum over the isotypic components of the isotypic component of the space of cusp forms on this space here for a given irreducible unitary representation in the unitary dual of 0M. This is well known. So if you would like to understand this, you have to show or determine first which representations pi have a chance to appear here as an isotypic component. And in particular, do they have non-vanishing relative Lie algebra cohomology? And secondly, if you want to know something about the size of the space, you have to know what is the multiplicity with which these representations occur in the Cuspidal spectrum of gamma n. I need one more information regarding the cohomology of the phase. The Lie algebra cohomology of the unipotent radical is a natural M module. And following the work of Constant, it decomposes as a direct sum of irreducible finite dimensional modules of highest weight mu W. And the W range over the minimal coset representatives for the left cosets of the full Y group, modulo the 1 of P, which is essentially given by this Y group here. And F mu W denotes the irreducible finite dimensional module of highest weight mu W. And mu W is given by essentially W applied to the highest weight of E, the coefficient system, plus rho P. Oh, the 0 has to be discarded. I'm very sorry. Minus rho P here. And yeah, okay. And the weights are all dominant and distinct. And moreover, for a fixed degree Q, only the weights mu W with lengths of W is equal to Q occur in the decomposition of the cohomology groups. So we are talking about cusp cohomology. And if you look at the case of the special linear group, then the Levy components have a decomposition in various blocks. And these blocks are all of type SLM plus minus, let's say. So you have the determinant plus or determinant is equal to plus or minus 1. So we first have to know what is the cuspidal cohomology of GLN or SLN. And it's an old theorem. I think the first one who observed this was Bill Kesselman, but he never wrote this up. And it's not so easy to prove. It's that up for a fixed coefficient system E, up to infinitesimal equivalence, there's at most one irreducible unitary representation sigma of GLM of the reals, such that the relative Lie algebra cohomology in the infinity vectors tensor E is non-vanishing. And sigma, H sigma occurs with non-zero multiplicity in the cuspidal spectrum. And this representation is necessarily tempered. If you ask for the same result for the case SLN, you just have to replace 1 by 2. Otherwise, everything reads the same. Due to the fact that this representation is tempered, the vanishing Lie algebra cohomology outside a certain range vanishes, and this range is centered around the middle dimension of the symmetric space attached to SLN. So the upper bound we are interested in is for M even given by M plus 1 to the square minus 1 over 4 minus 1, and for M odd by M plus 1 to the square over 4 minus 1. So what do we observe? I said before, in terms of differential forms, Eisenstein cohomology classes come from cuspidal forms on the faces, which means to have a class in the top degree of the cohomology of gamma, I need to have a cuspidal cohomology on the face in the top degree. But we observe that, for example, for M larger than 3, the cohomological dimension of GLM is M times M minus 1 over 2, is larger than the upper bound for the cuspidal cohomology. Only for M equal to 2 or 3, we have equality. This means, as I said before, to have an Eisenstein cohomology class in degree cohomological dimension, we need a cuspidal class in here. We saw before, this is a direct sum over all cuspidal cohomology classes degree P with values in HQ. And P plus Q has to be equal to CDQ. So if we look at the degrees here, if the cuspidal cohomology plus this degree here doesn't match the cohomological dimension, then we don't have a chance to construct an Eisenstein cohomology class. Or otherwise said, if the cusp cohomology doesn't exist in the cohomological dimension of gamma m, then we cannot reach the cohomological dimension of gamma. So this only works if P is equal to the cohomological dimension of gamma m and Q is equal to the dimension of n modulo gamma n. So just as an example, take the minimal parabolic P0. Then the space here consists of finitely many points. And here you have the cohomology of the unipotent matrices, the upper triangular matrices with ones on the diagonal. So the dimension here is n times n minus 1 over 2, which is exactly what you need here on this side. Yeah. So this simple observation, this is the case P0, okay. Yeah, simple observation leads immediately to some vanishing result for the summands which are attached to specific parabolic subgroups in the full cohomology. So let me talk a little bit about parabolics for SLN. So we take the minimal one of Borel subgroup of upper triangular matrices with maximal split torus, the group of diagonal matrices, determinant 1. We take the simple roots, usually labeled alpha I, and EI is the projection to the east component of an element on the diagonal. And the GQ conjugacy classes of parabolic Q subgroups of G are in bijection with the subsets J of the simple roots. And I denote by PJ with the Langlands decomposition or the Levy decomposition LJ, NJ, the standard parabolic subgroups attached to J. And the roots of LJ are those roots whose simple components are in J. Just to give you an idea how the parameterization works. So let's take the first case. The first case is the conjugate class of the minimal parabolic. This corresponds to the empty set in the set of simple roots. And the minimal coset representatives is equal to the Y group of W. And the longest element in there has the length, the dimension of the unipotent radical, which coincides with the cohomological dimension of gamma. Therefore, F mu W B is equal to the cohomology in the degree we want of N0. And case 2, we define the following family of non-empty sets. And before I go into these technical details, I just say this is a family of parabolic subgroups which are not the minimal one and only contain blocks of type SL2 or SL3. So one has to phrase this in more technical terms. So one takes the sets J subject to the condition that if you have two subsequent simple roots in there, then the next one is not permitted anymore. Because if it would be permitted, then you have an SL4 in there. Yeah. This is, if you have these two already in there, you have SL3, and if only one is there, then it's SL2 if the next one is missing. So this condition assures that only blocks of size 1, 2, or 3 make up the Levy subgroup Pj. So if I add up all the two blocks, which is the upper bound I had before for 2, and this is upper block 3. Oh no, sorry. This is the number of 2 blocks. The number of 3 blocks, and here you have dimension of Nj, you have exactly the cohomological dimension of gamma. So, by the simple observation I had before, you take the summand in the decomposition of the Eisenstein cohomology with regard to the associate classes, parabolics, then this vanishes if P is neither a minimal parabolic nor conjugate to one of the standard parabolics in this set labeled script J upper CD. This is just an observation as simple as possible. And I could have made it 30 years ago. So, of course, you are interested now what happens in the cases which are here as exceptions in the first statement. So we take the case of the minimal parabolic. And I just have to go back to my early years in Bonn as a graduate student. So we take a congruent subgroup, let's say of level P to the power u, and we exclude P equal to 2. Then the space of cohomology classes in the cohomological degree, the top degree, which restrict non-trivially to the cohomology of the phase in the associate class of minimal parabolics, has a dimension which is larger than the right-hand side here. So if you're interested to see the details, just look in my thesis, written in 1977. Sorry that I talk about these old things, but I was happy to see that Mikey even mentioned the year 1976. So, okay. So it's eine Kontrahendu-Note oder Bonner mathematische Schriften. And how to prove it? Just for those of you who are a little bit familiar with the construction of Eisenstein cohomology classes, you have to pass to the adelic setting here, which means you have to look at all gamma conjugacy classes of minimal parabolics at the same time and put them together in an expression. You take a maximal torus in there and mod out some open compact subgroup and the rational points of the torus. Then you take the zero component, and you have to, the role of cusp forms is played by characters. Then you have n-1 different characters. And to these you attach an Eisenstein series. And you have to evaluate this Eisenstein series to get a non-trivial cohomology class at the parameter equal to 1. In terms of roots, this is the parameter rho P0. Yeah. So the question if the Eisenstein series is holomorphic at this point or not is decided by the constant Fourier coefficient of this Eisenstein series. And if you follow the Langlands-Shahidi method, you see that you have ratios of L functions in there. And the ratios of L functions in this case are coming all with the characters, chi1 to chi n-1. And you have to evaluate this at the point 1. So if the characters are non-trivial, you are fine, because then the Eisenstein series is holomorphic at this point. And what you have on the right-hand side is just counting the number of characters and the number of gamma conjugacy classes of the minimal parabolics. This is done at that time. Of course, you can even do better by the same type of argument. You can decrease the degree here and do similar things. But in the moment you have one character on this side of these n-1s, which parameterize the Cuspidal forms on the torus, is trivial, then of course you are in certain danger, because the Dirichlet L functions can have a pole at this point 1. But it doesn't have not always a pole. This is a subtle question which still deserves to be elaborated, but not in this talk here. Okay, so we have dealt with now with the minimal parabolic. We have this result here. And now we go to a parabolic, which is conjugated Pj. And we take J is given by these simple roots, A1, alpha A1 to alpha A R. And the usual condition I had before, that if alpha I and alpha j are in J, then the difference of the indices has to be larger or equal than 2. So if we take a torsion-free principal congruent subgroup, then the following result can be proved. The component attached to this parabolic given by J decomposes over the gamma conjugacy classes in this associate class. And here I have an index E prime Q now. So this summoned here are those Eisenstein cohomology classes for each of the faces, E prime Q, Q in the associate class. There's something missing. No, sorry. So these Eisenstein classes are originating from cusp forms on exactly this face. So I fix the gamma conjugacy class, and I fix the face, and I take all these Eisenstein cohomology class. So the result is, this is non-trivial, and its dimension of the left-hand side is now given over the number of gamma conjugacy classes of P times the G conjugacy classes of P times the dimension of the cusp cohomology of the face. The first one is easily determined, namely it's n minus r over r, where r is the number of simple roots you are looking at. So we have to determine the number of gamma conjugacy classes on the dimension of the cusp cohomology of this space here. So the first lemma is if gamma is gamma q, q is a prime power larger than 2, then this number is given by this expression here. So we take 1 over 2 to the power n minus r minus 1 times the product over all these factors q to the power I minus 1 from I equal to 2 to n modulo q to the power minus 1 bracket r. R is the number of simple roots. Okay, so this is done. And now we have a specific case, just to show you how the various ingredients in the result I showed you at the beginning as an illustrative example come together. Just take the case where J consists of one simple root. This means that the Levi component of our parabolic consists of one SL2R plus minus 1 times plus minus 1s plus minus 1s, etc. So the cusp cohomology is then computed as the cusp cohomology in degree 1 of the congruent subgroup of level Q in SL2 plus minus 1 with coefficients in the coefficient system given by the highest possible weight in the decomposition with respect to the M-module structure of the Lie algebraic cohomology of M. So following Eichler-Shimura isomorphism, this is isomorphic because this one here turns out the trivial representation is isomorphic to the space of cusp forms of weight 2 plus the conjugate of this one. And if you, of course, we know the dimension of this on the right-hand side, because the dimension of the space of cusp form of weight 2 is equal to the genus of the compact Riemann surface attached to delta Q. So we have a precise result about the size of this cohomology groups. So we can plug this in. No, sorry, this was too far. We can plug this in into the general formula I had before. Here. We have this one here. This is determined. This is determined. And of course, now we have also this one. So in the case, if J is just one simple root, we have a precise formula. Of course, if you have now, let's say, 2 SL2 components or 5 SL2 components, you can also work this out in detail, and you get the formula I had in the beginning as this example. Yeah, I don't want to give the details here. One remark: in treating the case of the minimal parabolic, we had to pass to the idyllic setting. But in this case, you don't have to do this, because we are in the top degree, which means the Eisenstein series we are constructing, we start with some differential form of E prime P, whose coefficient functions, if you express it in terms of some Maurer-Cantin frame, are Cuspidal functions, okay? And you form the Eisenstein series, and you have to evaluate it again at the point rho P, okay? But then comes really the hard work. Namely, you have to show now, that the Eisenstein series doesn't have a pole at this point. And you can do this with some, really have to go quite deeply into theory of Eisenstein series to work this out, but it's correct. And which means that all the classes on this side here, yeah, give rise to cohomology classes here. Of course, you have to be very careful that you different Cuspidal classes don't give the equivalent Eisenstein cohomology classes, but this can be handled by looking at the restriction of the class you get here back to the faces. So this is, in some sense, to bring things a little bit together. You have a simple observation. You just find out which parabolics can contribute to the Eisenstein cohomology by figuring out for which parabolics the Cuspidal cohomology lives high enough. And then you see if you can say something about the size of the Cuspidal cohomology of these faces. Okay, up to now, we only dealt with the case the blocks are of type SL2. So the next question is, what do we know about the case SL3? So, which means we have a parabolic, let's say for n equal to 5, we have one SL2 parabolic and one SL3 parabolic. Of course, the SL2 part can be handled exactly the same way as before. But in the case SL3, what do we know about the Cuspidal cohomology of arithmetic subgroups in here? And I have to say, when I worked with Ronnie Lee on these questions in, when was it? In 1980, 1981, 82, he said to me sometimes, you're obsessed by finding cusp forms. And in some sense it's true, but the success was minor because we could only do it in some tricky way. Namely, if you have a congruence subgroup where P is equal to 3 mod 8 and P is congruent minus 1 mod 3, then the dimension of the Cuspidal cohomology is larger or equal than P times P plus 1. And how do you prove that? Just to give you an idea how difficult it is really to get your hands on cusp form in an explicit way, in particular knowing how many you have. So to do this, we looked at the total cohomology of gamma P, just forget the cusp here, decomposed it in the Cuspidal cohomology plus the Eisenstein cohomology. Then we looked at the Cartan involution, which induces an involution on the cohomology. You can compute the Lefschetz number of this Cartan involution, and you compute the contribution to the Lefschetz number coming from the Eisenstein cohomology, and you take the difference, and we were happy that the difference was not 0. And then you can even do a little bit better. You just look at the representation theory of SL3 over the integers modulo gamma p on these spaces here, then you get a better result. So it's quite tricky. Other results of this type only give non-vanishing results by only, what you can say is, passing to some subgroups of finite index, you find some Cuspidal automorphic representations. And but you have no idea how large the space, for example, is if you fix the level gamma p. So I just realized that I'm very fast. Do I speak too fast? I hope not. So let's go back to other cases and see if you can generalize this observation. So we started off from the Cuspidal cohomology plus the Eisenstein cohomology, decomposed along the different associate classes of parabolic subgroups. And we tried to see, first of all, what is the contribution of the cusp cohomology to the total cohomology? So you can always fix, of course, the degree here. So let's first talk about other groups in SLN. So you take still the cohomological dimension here, then you take the cohomological dimension here. So you ask in which cases you have Cuspidal cohomology in this degree, which means you have to do the same as we did for GLN or SLN, determine the Cuspidal automorphic representations which have non-trivial GK cohomology. This is possible and this is done. So you can say exactly what happens here. But if you ask already what is the size here, what is the multiplicity, then you don't have many results. So if we are here and we take one of these summons corresponding to an associate class of a parabolic, you, as we have seen, you are reduced to the same type of questions for a Levi subgroup of this parabolic. We have a classical group here, let's say for G, then the Levi parabolic here is or decomposes as a direct product of classical groups of the same type you started with, times some GL M's, different M's, of course. So the same question we had already here, let's take, for example, the symplectic group. You have here the symplectic group, and here you have symplectic groups of smaller rank. So you can do the same game as we did before. And if you have results about the Cuspidal cohomology of SPM, for example, times GL5 or whatever, then of course you can do the same game as I did in the case SLN and lift everything up. This works perfectly fine in the cohomological dimension. So this is first, as I discussed, the range of the Cuspidal cohomology. And in the case of the minimal parabolic, of course, you have to do what I did before. You have to pass to the adelic setting and do all the usual thing, determine the holomorphy or non-holomorphy at specific points of the Eisenstein class attached to rank -1 characters, for example, or rank D characters. And in the case G2, you have to determine associate classes, etc., etc. Of course, you can do the same if you change the degree here, but then the lower you get, the more you have to be aware that the Eisenstein series you construct and you have to evaluate at a uniquely determined point is not holomorphic. So it means it has a pole at this point. And then, of course, this is something which is really current research, and yeah. And I think this is all what I wanted to say at this point. Of course, this talk didn't have anything to do with theta series, the topic of the conference, but I think it had something to do with the joint trajectory of Steve Kutler and myself. We went through together, and so I think it's an appropriate topic for a talk. And if you would like to see details, you just look in the forthcoming publication. And thanks to Steve for a very long friendship, and thanks to you for being in the audience.
All right, let's thank Joachim for a very nice talk. And does anybody have any questions or comments for Joachim?
So what are other cases that you can do? I mean, you said something about symplectic and.
I didn't do the symplectic case yet, but if you force me to do it, I do it.
Well, your own boss.
Yeah, I mean, it's, how to say, from my point of view, it's not too difficult, I would say. Yeah, so if you're really interested to have explicit results about the size of these cohomology groups, you can do it. And but the questions for me are quite natural and not too difficult to resolve, I think, if you have enough information about the Cuspidal cohomology of the Levy components. If you don't have, then there's no chance. So for example, I mean, you can look, of course, at the split group G2. Yeah? The Levy components which appear are of type GL2. So you can do exactly the same what I did here. Yeah. And I can write you down the size of a congruence subgroup or the arithmetic subgroup defined by some congruence conditions. This is exactly the same way as I did it here. Or you can do it. There's another aspect where I think I should mention. You can ask what's happened, for example, for the full group SLN over the ring of integers of some number field. These groups have torsion, but constructing Eisenstein series on the level of differential forms, which are forms on X being invariant under gamma, yeah, they don't, nothing changes if you allow torsion, yeah. So the only thing what you have to be a little bit careful about is how the center of the group acts on these things. Yeah, this makes a slightly subtle point. But otherwise, you can also construct for GLN or SLN O Eisenstein cohomology classes over some number field. And the number you get is then, what is it? Class number of the underlying number field, I think -1. This is the number of characters. No, class number -1 in bracket to the power n-1. I think this is at least what you get from the minimal parabolic. And if you do the SL2 part, you can do better, I think. Yeah. Okay.
You can also do F4. I think there is the levies are not that.
Yeah.
Strange, I mean.
Yeah.
When you say cohomology, of course, you mean just singular cohomology, right? Without any support and so on, right?
Yes. Yeah.
My question is, I mean, what happens if you impose, I mean, in other words, if you look at some different kind of cohomology?
For example, which one?
Well, for SLN, I'm not so familiar with Shimura varieties. You have intersection cohomology, you have inner cohomology, you have, I mean, there are all sorts of cohomology theories. And,
yes, okay. So let's talk about the inner cohomology. Yeah. So we had the Borel-Sacks compactification is a compact manifold with boundary. Yeah. So you look at the long spectral sequence in cohomology attached to this pair of the cohomology of the space modulo the boundary, and then the inner cohomology or interior cohomology is defined as the image of the relative cohomology in the total cohomology. And this is sandwiched between the Cuspidal cohomology on the left-hand side and the L2 cohomology on the right-hand side. L2 cohomology now defined as being, if you speak about it in relative Lie algebra terms, as the image of the relative Lie algebra cohomology with L2 coefficients in the usual relative Lie algebra cohomology with C infinity coefficients. So the Eisenstein series live, of course, outside the inner cohomology, yeah, whereas the Cuspidal cohomology lives inside.
Okay.
What about others like coherent cohomology? I have to think about, I think.
I mean, of course, inner cohomology is not a cohomology theory, so
That's true.
it's not. I don't like it. I know Günther is listening here.
But you asked for that.
I agree. Yeah. So inner cohomology is not. I think you have to look at the long exact sequence, and so you. The cohomology with compact subs is sitting in this long exact sequence, and if you want to study that, again, have to use Eisenstein series.
Well, for instance, does your thing say anything about cohomology with compact supports?
No, this is dual to the cohomology. So there's pointer duality between between cohomology with compact supports, and so if you have vanishing theorems above a certain degree for the cohomology, you have vanishing theorems for inner cohomology, for compactly supported cohomology in low degrees. Huh?
Yeah, correct.
I see. Okay.
You see?
But you can, I can also add another remark. I mean, if you're interested, for example, just look at the cohomological dimension. Where is it? Yeah, the cohomological dimension, and we have the parabolic, the minimal parabolic, yeah? And you look at the contribution to the cohomological dimension. As I said before, only where you're really on the safe side is you take all characters, chi1 to chi n-1, being non-trivial. Yeah. But of course, there are other classes attached to these characters, even if one of them or more of them are trivial, which can also contribute to CD gamma. This has to do with the kernel of certain local intertwining operators. Because it can happen that the pole which occurs in one was originating from one of these, usually L series attached to a character, is killed by the kernel of this local operator. So to determine exactly the size of the contribution of the minimal parabolic, yeah, is still open problem. And I have to confess, even in the public, this was the topic Günther gave to me as a thesis project, and it's not done. Sorry.
Okay.
As Mikey said, we give it to the next generation.
Oh, yeah, no.
All right. Do we have any more questions or comments for Joachim? Then let's thank him again.